Let me ask you something. Have you ever tried to compare two numbers, say, the number of apples you and your friend have? Maybe you had 5 and they had 8. You'd instantly say 5 is less than 8. That's the beginning of inequalities in mathematics. Unlike equations, where both sides are equal, inequalities help us show when one quantity is smaller or bigger than another. We use symbols like less than, written as the angle bracket opening to the left, greater than, written as the angle bracket opening to the right, less than or equal to, with an underline, and greater than or equal to, again with an underline. In this chapter, we'll learn how to handle such comparisons algebraically, solve inequalities in one variable, and express their solution using set notation or on a number line. Let's dive in. Let's start with the first kind of inequality, when A is less than B. This is written as a angle bracket opening to the left B. It simply means that the difference B minus A is positive. Let's look at some examples. Take 2 and 7. 2 is less than 7 because 7 minus 2 equals 5, which is clearly a positive number. Here's another one. Negative 5 is less than 2, since 2 minus negative 5 becomes 2 plus 5, which equals 7, again a positive number. Even with fractions, the logic holds. 2 by 3 is less than 4 by 5 because 4 by 5 minus 2 by 3 gives us 12 by 15 minus 10 by 15, which equals 2 by 15. Positive again. So, the takeaway here, if B minus A gives a positive result, A is definitely less than B. Now let's move to the second type, when A is less than or equal to B. We write this using a less than sign with a horizontal line below it. This means that B minus A is either 0 or positive. Here's an example. Negative 3 is less than or equal to 5 because 5 minus negative 3 equals 5 plus 3, which is 8, a positive result. Now take 2 by 7 and 2 by 7. Clearly, they're equal. So 2 by 7 is less than or equal to 2 by 7 because the difference is 0. This inequality type allows room for equality, unlike the strict less than symbol. Alright, moving on to the opposite idea, when A is greater than B. This is written using the greater than symbol, angle bracket opening to the right. This time, we say A minus B is positive. Try this. 7 is greater than 2 because 7 minus 2 equals 5, which is positive. What about negatives? Let's test negative 2 and negative 5. Negative 2 is greater than negative 5 because negative 2 minus negative 5 equals negative 2 plus 5, which gives 3. Still positive. Even for fractions, it's the same logic. 4 by 5 is greater than 2 by 3 because 4 by 5 minus 2 by 3 equals 2 by 15, positive again. This rule holds for all real numbers. Now let's discuss A is greater than or equal to B. This is written using the greater than symbol with an underline below it. It means A minus B is either positive or 0. For example, 5 is greater than or equal to negative 3 because 5 minus negative 3 equals 8, a positive number. If both numbers are equal, like 2 by 7 and 2 by 7, then the difference is 0, and that still satisfies the condition. This form, like the previous one with less than or equal to, includes equality as well as greater than conditions. It's frequently used when dealing with ranges or limits in inequalities. Let's switch gears now and see what inequalities look like geometrically on a number line. Suppose A and B represent numbers A and B on the number line. If A is less than B, point A lies to the left of point B. If A is less than or equal to B, then point A is either to the left or exactly at B. On the other hand, if A is greater than B, A is to the right of B. And when A is greater than or equal to B, A is either to the right or coinciding with B. This visual representation really helps make inequalities more intuitive. The number line provides a simple but powerful way to understand inequalities and compare values in a glance. Let's quickly revise what we've learned about inequalities. We saw that inequalities like less than, greater than, and their inclusive versions help compare values when they're not equal. These inequalities rely on the difference between numbers, specifically whether that difference is positive or zero. We looked at both integer and fractional examples, confirming that the logic applies across all real numbers. And we visualized these relationships on a number line to reinforce the concept spatially. Inequalities are foundational in algebra, helping us define solution sets, ranges, and constraints in equations. I hope now you understand how real number inequalities work and why they're essential in algebra. Finally, we saw how to represent solution sets using number lines, set builder, and interval notations. And that wraps up our journey through linear inequations. In the next video, we discuss solving linear inequations in one variable, where we go deeper into how to isolate variables, flip inequality signs when needed, and represent the final answers with clarity. Until then, keep practicing and stay curious. See you soon.